I'm going to prove the fundamental theorem of algebra, which is every non-constant polynomial has a root in C. You normally hear it slightly differently, but if you can find one root, you just divide out by z minus r, and that's going to give you a polynomial. It's going to give you a polynomial of degree n minus 1, if this had degree n, and then you can apply the same theorem again, and you can get that this new polynomial has a root. And so you can keep on doing that n times, and then after n times, you're going to have degree 0, which is constant. So you can find n roots. And the proof is by contradiction. So suppose, apostrophe, f of z not equal to 0 for all z belong to C. Well, if that happens, then 1 over p of z is a rational function where the denominator is never 0, so this thing is entire. So I can compute, using the Cauchy integral formula, I can compute the integral around a circle of radius r. So I'm going to look at this circle of radius r centered at the origin of, I'm going to compute 1 over z p of z dz. And that's going to be equal to, well, c of r, the only bad part, right? 1 over pz is holomorphic everywhere. It's entire. So this has f of z over z minus w form, which means that it's equal to 2 pi I times f of 0, where f stands for the denominator, or the numerator, sorry, which is 1 over p of 0. So I can solve for that. But notice that in here, right, p of 0 is easy to compute. 2 pi is a constant, 1 is a constant. This doesn't depend on r at all. So I can take the limit of bigger and bigger circles. The limit as r goes to infinity. This equals the limit as r goes to infinity. This equals something that doesn't involve r. That equals something that doesn't involve r. So for every single circle, no matter how big you make it, the answer, whenever you integrate this, you're always going to get 2 pi I times 1 over p of 0. Well, let's also think about this. Let's compute this integral, but by bounding it, right? So this is going to be less than or equal to the max value of 1 over z p of z on the circle times the length of the arc. Well, this is a full circle, so it's just going to be 2 pi times r. Well, we need to find the maximum value of the length of the circle. So going over here, I get 1 over z times p of z. Oh, but on the circle, right, so I can split these up. On the circle, the modulus of z is always going to be r, because I'm exactly r away. So that's 1 over r times the modulus of p of z. But p of z we can bound. We have this lemma that says that, by the way, I'm going to replace this with something smaller, making it bigger. We know that 1 half times the leading coefficient times a to the d, or z to the d, is less than or equal to p of z, where as long as p of z is equal to a to the d, z to the d, plus smaller terms. So this is equal to 1 half times a of d times z to the d, which equals, but the z is r, so this is equal to 2 over r to the d plus 1 times the modulus of ad, which is just a constant. So this is equal to 2 over a whole bunch of r's, d plus 1 times this thing, a to the d, whatever that coefficient is, and that's just going to equal something over a bunch of r to the d's, which goes to 0. I'm going to have to stop and pick up this one little bit, so I'll make this part 2.